Thank you. It's a pleasure to be here with so many friendly faces and to be giving a talk. Now that I lured you all here with the title about the Milky Way and fundamental astrophysics, I'm going to focus on one very particular thing, which is how we can use surveys like Gaia. This is an image produced by the Gaia mission. How we can use surveys like this to understand one very small part of astrophysics, which is dark matter. So before I get into the details of that, though, I wanted to give you a sort of sense of who I am as a scientist and what my broader interests are before we focus down on one particular subject. And so most of the work that I do sort of works at this interface, the intersection between gravitational dynamics and statistical inference. And there's a pretty broad set of problems that fall into that region. So you can sort of think of the different things that I've worked on as grouped into a few different themes. One of those themes is what I'm going to focus on here, which is trying to understand dark matter theories. And the main science question that I'm interested in is what are the galaxy scale properties of dark matter, which I'll often call small scale without thinking about what that actually means. Another main theme of my research is galaxy evolution, or for me, more specifically, I mean how the Milky Way has been assembled, how the stellar mass in the Milky Way, the different components of our galaxy have been assembled or accreted, or formed. And then for something completely different, a third thing that I'm interested in is star formation and exoplanets and binary stars. And the main question that I'm interested in and working on right now is how do binary star populations vary throughout different environments, throughout the Milky Way, throughout chemical environments or dynamical environments. And as I said, I'm not going to talk about either of these pretty much. I'm going to focus on just one theme, which is what we can learn about dark matter on scales of individual galaxies using the Milky Way and contemporary surveys. So I'm going to very quickly go through this, since many of you are experts on the broader cosmological theory. But lambda cold dark matter, so our cosmological model, is very successful on large scales. So if you take the initial conditions, the density fluctuations inferred from the CMB, the cosmic microwave background, you run a large-scale structure simulation, you end up seeing structure that looks a lot like what we see in the real universe as traced by, for example, galaxies in the cylindrical sky survey. So that's good. It's very successful on these sort of cosmological scales. But if you zoom in to one of these halos that form, and you want to ask, does the theory do a good job of predicting things that happen on those scales, then the question is harder to answer. I don't have an answer for you, and for two reasons. One is the predictions are not as hard, so there's sort of weaker predictions that vary depending on what prescription you look at for the simulation you're using or what tracer you're using. To sort of illustrate that, this is Milky Way mass dark matter halo simulated by the FIRE collaboration. So this is zoom in on a single galaxy. This is the dark matter density distribution. This is a dark matter only simulation. On the right is what happens if you include the formation of a galaxy, star formation, etc. So there's differences between dark matter only and when you include physics. And then there's differences in the predictions that these types of simulations make depending on how much physics you include, what prescriptions you use, etc. There are some broader or weaker predictions that are sort of consistent between these theories or these simulations. And so those are the things that I'm interested in testing within the Milky Way.
And those are literally identical initial conditions?
Well, depends on how you define identical, because this has baryons and this doesn't.
But very similar initial conditions.
Yeah. So yeah, you can see some broad differences. Like this is a zoom in of the inner regions. This is the dark matter simulation is more triaxial, has more of a cusp. Here there's more of a core. It's a lot rounder. The isodensity contours.
And you're showing the dark matter over here as well.
That's right. It's dark matter in both.
Differences in the dark matter. That is a very stark demo of these issues.
So, how much do you trust these simulations?
That's why I'm saying they're weaker predictions.
Because, if as a sort of dynamicist, you want to make sure that you get orbit integrations right.
Totally. And that's why I'm only going to focus on two predictions that seem to be generic. Or things we can test. They're not even predictions, they're just things we can check for. One is this so-called universal density profile that dark matter tends to have on large scales. So if you zoom out in one of these halos and just look at the outer mass density profile of dark matter, it tends to follow this Navarro-Frank-White NFW profile. So around the Milky Way, beyond the sort of radius where baryons dominate, the mass density should fall off like 1 over r cubed, roughly. Another thing we can check is the existence of dark substructure or low mass substructure. And this is particularly interesting, not because even baryonic simulations show the presence of dark substructure, but because the properties of substructure change depending on what dark matter theory you look at. So this is the number, it's like a halo mass function as a function of mass for different dark matter theories. This is just a cartoon. But in the case of cold dark matter, you expect power on all scales, and you expect many more low mass things than high mass things. Other dark matter theories like fuzzy dark matter, warm dark matter, self-interacting, etc., typically all have some truncation or cutoff to the mass function, below which you don't expect to see massive substructure.
Those theories are extreme. What about more conventional things like neutrino mass? Neutrino mass is also like a warm component.
Yeah.
Does that
So
also have an effect?
You can change the mass of the particle and move this truncation.
But what about if you have a small admixture of something warm? Is that also going to be testable in this?
Yeah, then it's muddier. Then it's all in the details of what's the actual mass function. So there's the zeroth order test, which is, are there things down here? And then there's the question of what the abundance of those things is, and that is more discriminated.
So Adrian,
Yeah.
the warm dark matter depends, the cutoff will depend on the mass of the particle, right?
Exactly, yeah. So we know the Milky Way probably has a substantial dark matter halo, so it's no coincidence that all of the theories tend to say that there's dark matter on those scales. We also think most of the dwarf galaxies around the Milky Way have dark matter. Their kinematics are dominated by large halos. So we think this range is sort of probed by dwarf galaxies. Below that range, this is where a lot of the discriminating power comes in for different dark matter theories. So are there things on these mass scales? So for this talk, I'm going to focus on three questions. One is, why am I talking about this now? So why do the astronomical surveys, the data that we have in hand right now, or will have within the next 5 years, why do they enable new tests of these dark matter theories, or these weaker predictions? How can we even do this? How can we use a single snapshot of our galaxy from these surveys to learn about its mass distribution and its history? We're using one snapshot in time to learn about dynamic things. And the trick there is to use the type of object that I'm going to talk for most of the talk about, which are stellar streams. And then the last question I want to focus on is how we need to improve the models that we have for the formation of these streams in order to make precise inferences about dark matter, the fundamental nature of dark matter. And the spoiler is that there are no simple stellar streams from looking at the data, and so we need to have more sophisticated ways of modeling them. Very briefly, I wanted to give a shout out to the fact that all of the science and the figures in this talk were made possible by open source software. So I'm a big believer in open science in general and open source software. I'm a core developer for the AstroPi project, and I maintain a package called Gala for doing galactic dynamics and orbit integration and things like that. And so most of the figures were made possible because of this piece of code. Everything else that I do is made possible from this large collaboration. Okay, so let's get back to dark matter. So why are the modern surveys that we have of the Milky Way so transformative in terms of the data that they're providing? So to get into that, I want to start with a very brief tour of the galaxy. So historically, and I would say before April 2018 or so, most of what we've come to learn about the structure of the Milky Way, the different components of the galaxy, have come from purely photometric surveys with some sparser follow-up from spectroscopic surveys that give us some idea of the kinematics, but very sparsely traced throughout the galaxy. So from photometric surveys, we think that the Milky Way looks something like this galaxy, NGC 6744. So we think the inner regions are dominated by a bar-like structure that is maintained through the orbits of stars that are in the inner regions of the galaxy, maintain a sort of rigid body that rotates with some pattern speed. And that's interesting dynamically for stars in this other component, the disk, because it ends up being a time-dependent component to the gravitational acceleration field, and so it can have a strong effect on the orbits of stars even much far beyond the radius of the bar. Then there's the disk, which is where most of the stellar mass is in the Milky Way. And then the thing that you can't see here is the much more diffuse stellar halo, which essentially goes to the edge of the galaxy It's much lower density on average and contains pretty much mostly accreted material from other galaxies that have merged with the Milky Way.
Is that a dwarf at the end of that arm?
Yeah. This is a stream, essentially.
Mm-hmm. And there's an arm pointing right at it.
Yeah, I literally think this is like the Milky Way, including that.
Mm-hmm.
And notice this is not a cartoon that was drawn by someone at NASA.
It's got a nice bar ring structure.
Yep.
Too.
To scale, we think the sun would sit somewhere about here relative to where the edge of the disk is and the angle relative to the bar and the size of the bar. So we know all of this about the Milky Way, or we think that this is sort of the static picture of what the Milky Way looks like. And I'm very excited about the current surveys that are happening, primarily because of the Gaia mission, which many of you are experts on, so I won't belabor it too much. But by end of mission, so Gaia was launched in 2013, and it's primarily an astrometric mission, so it's measuring the proper motions, the parallaxes of about 2 billion stars. It's also getting spectrophotometry, photometry, radio velocities for a subset, but still a pretty large subset of the stars that it can see, and it's all sky. So we'll go from having this sort of static picture of the structure of the galaxy to being able to understand the kinematics of these different components of our galaxy. And if you're interested in main sequence stars, which is where a lot of the density is, the effective volume of Gaia relative to the size of this other lookalike galaxy is a few kiloparsecs or so. So it's still a substantial part of the disk, but it's fairly still close to the region around the sun. The key for Gaia is that if you go to intrinsically brighter stars, you can essentially see the entire galaxy up to the edge of where we expect dense stellar populations to exist. So this is end of mission. In hand right now, we have data release 2, which was released still less than a year ago. There'll be more data releases roughly once a year for the next few years, and then there's a mission extension, which will continue going and improve the quality of all of the data that we have. The key point, though, is relative to its predecessor, we now have a lot more volume, we have more precise data, and we have time domain information. And so the hope is that we can take this, even though it's a single snapshot of the Milky Way, kinematic information, use it to learn about the dark matter structure on the scale of the Milky Way. Of course, we don't actually observe the dark matter, though. We only observe the stars. And so we get astrometry and maybe spectra for about 1 billion stars from a mission like Gaia. And this is in the form of a graphical model because it's about to get a lot noisier here. But you can read this as we have data. So the shaded thing means we observe those things. We have about 1 billion data points from Gaia. That data is produced, if we knew the true kinematics
I'm
right
glad
now.
you started at equals 1,
Say
not
again?
0.
What did you say?
Glad you started at equals 1, not 0.
It's too bad you added that because it was such a great graphical model before. Like, I could totally execute that.
Yeah, I mean, this is Gaia. The rest is just what we think we can do with it. So if we had an instrument model and we knew the true kinematics and the true chemistry, we could produce the data that Gaia observes. So the arrows you read as generate. So if we had an instrument model and we had kinematics for each individual star, we could generate the data that we observe. That's not very interesting, because if we had all the true things here, then we wouldn't need to learn anything. All of the interesting physics, though, is what goes into generating these true quantities, which then produce the data. So you can think of all of astrophysics in the context of what we can learn from the Milky Way as a statistical generative process, one component of which is the dark matter, but there's a lot of other things going on here. Some of these things have good theories or good models that we can directly test with parameters we can plug in and see what things come out. Some of them might be mythical creatures. There might not be a concise theory for galaxy evolution that we can just put in and directly test. Might be more stochastic. But notice that all of these things are extremely connected. So if you really want to learn about the data that we have and use that to constrain dark matter, you have to basically infer all of astronomy and then marginalize it out and then constrain dark matter. And since that's a hard problem, I'm going to just focus on that branch. So I'm going to cut out the left branch here, which is still hard, both statistically and dynamically, and say if we have the data for some population of 1 billion stars in the Milky Way, can we simultaneously infer the latent variables, which are basically as numerous as the data points we have, and use those latent variables to then infer properties of the dark matter in the galaxy. So statistically, it's hard because we have basically as many latents as we do data points. Dynamically, it's also hard. So we're trying to take the instantaneous, so at today, phase space distribution function, so position velocity for all the stars that we observe. We're trying to use that to learn about the underlying force field. And unless you make very, very strong assumptions, there's no necessary connection between those two things. You have some tracer population and you have some underlying force field. So you can make very strong assumptions and say that they're related in some way, and then you can do inference. But just as it is, that actually doesn't give you any information about dark matter. If you had, instead of the instantaneous distribution function, if you had like orbital information, so if you had positions and velocities as a function of time, that would be a little bit easier. Still hard, but it would be a little bit easier. In astronomy, though, as all of you know, we never actually see a full orbit through the galaxy. But I'm going to talk about a class of objects that does give us information about orbits, and thereby makes this problem a little bit more tractable. The other assumption that I'm not going to really talk about, but that I tend to make sort of implicitly in a lot of things that I do, is that you can decompose the overall acceleration field of the Milky Way into two components. One that's sort of the global dark matter distribution that's maybe adiabatic or roughly static and could have some arbitrarily crazy shape, but that describes the global distribution of dark matter. And then there's some time-dependent explicit substructure component to that. I can also show you why we know that this is wrong, but that I will still make that assumption for the next few slides at least. So how can we get at this orbital information from a snapshot and then thereby making this problem of turning instantaneous observations of the Milky Way into dynamic inferences about the structure of dark matter? And to do that, I want to talk about stellar streams. And this is really, that is the key reason that I'm so excited about these objects. So what is a stream? So here's a very, very simple simulation of a star cluster disrupting on an orbit around a very, very simple model of the Milky Way. So it's a spherical, time-independent, NFW, dark matter acceleration field, with a star cluster on the orbit that's shown in green. And as the cluster is orbiting around the galaxy, stars are tidally stripped from the progenitor cluster. The stars that are stripped are colored in red or blue, depending on whether they end up leading or trailing the orbit of the cluster. So the stream is the entire thing, but you can think of it as two components, a leading component and a trailing component. So you can think of why this happens. Why does it form leading and trailing tails from tidal stripping? You can think of it in terms of the restricted three-body problem. So we have a star cluster, this smaller mass M2, orbiting around the Milky Way M1. As it's orbiting, because it's a fairly fluffy thing, even a star cluster, stars can get stripped out through the Lagrange points, depending on the distribution function of orbits within the cluster and their evolution. Stars will end up coming out of L1 and L2, which sit roughly at the tidal radius of the cluster, or the Jacobi radius. From this, you can then ask what is the gradient of the gravitational potential over from L1 to L2, and that gives you a sort of characteristic size or spread in energies of the stars that are stripped out. And so the fractional spread in orbital energies of the stars that are stripped out ends up just being the mass ratio of the satellite mass over the enclosed mass within the orbit to the 1/3 power. So if you look at systems that we see orbiting around the Milky Way, like globular clusters and dwarf galaxies, which we know form streams, for a globular cluster, this fractional energy is less than 1% or so. And this fractional energy tells you how fast stars are going to phase mix away, how fast their orbits are going to phase mix away from the orbit of the progenitor cluster. So that means, since it's so small for a globular cluster, the stars that are stripped have very small deviations in energy from the orbit of the cluster. It's going to take a very long time for a 2-pi length stream to form. For a dwarf galaxy, it'll take less time because there's a larger fractional spread in energy. That also means that the stars that come out roughly trace the energy or the orbit of the stellar cluster. So that means from a single snapshot, if you see the stream, you have information about the orbit that the cluster is on. And that's what we're after. thankfully, that's not just a theoretical idea. So this is a real stream in the Milky Way halo called Palomar 5. You can ask Sarah all about this stream if you want. So this is the globular cluster Palomar 5, sitting at a distance of about 22 kiloparsecs. This is the leading tail. So if you look at the orbit of the cluster, this is the forward direction. So this is the leading tail. This is the trailing tail. Does exactly what we thought from that simple theoretical idea. The two tails roughly delineate the future and the past trajectory of where the cluster is and where it's going, with interesting deviations that we can talk about at the end if you want. And that's not the only stream. We know of many others. So this is the Northern Sloan Digital Sky Survey footprint. It's a nice compilation by Anna Benazza showing some of the best studied streams, which I've labeled with arrows here. You can just make out this GD1 stream. So this is similar in size, in width, I should say, to Pal 5, but it's much longer. It spans almost 100 degrees on the sky now. I'll talk a lot more about that stream later. Then there's the orphan stream, and this mess, which we call the Sagittarius stream down here. So that was the SDSS view. We now know there's about between 30 to 60 at least. They're being discovered with an accelerating pace because we now have not only photometric information, like from SDSS, we have kinematic information from Gaia, and those two together let us characterize the sort of population of streams that we know about. So we know they're fairly metal poor relative to the sun and the disk. They have fairly large aspect ratios. They tend to be much, much, much longer than they are wide. And most of them tend to be found in the stellar halo, so between 5 and 100 kiloparsecs from the sun. And that's both an observational effect and a clue to their formation. It's easier to see things in the halo because there's a lower background or a foreground, however you want to think of it. The density is much lower in the stellar halo than it is in the Milky Way disk. It's also where these accreted things tend to disrupt because their orbits tend to be much more elevated than the typical star in the disk. Interestingly, though, this is also the region of the galaxy where, because the stellar density is so low, the dark matter density, or the relative contribution of dark matter is higher. And so from seeing the streams, we get information about orbits in the exact part of the galaxy where dark matter dominates the gravitational field. So that was realized a long time ago by Catherine Johnston, and actually David Spergel is a contributor to some of the initial work on that. And so since then, it's led to a whole enterprise, I would say, of trying to constrain the global distribution of matter in the Milky Way from modeling individual streams. And there's sort of three classes of ways of trying to do that. So the simplest, I would say, is you just assume all of the stars in a stream are on a single orbit, and you just fit in orbit and vary the gravitational potential until the orbit goes through all of the phase-space dimensions that you measure for that stream. So this is pretty fast, and it's been used for some streams, but it's wrong in detail because there could be energy gradients along the stream, and if you have a perturbed stream, which I'll talk a lot about in a bit, then this doesn't really make sense. Another thing that's been used, that's actually been applied to real data, is what I'm calling modeling the stream track. And where track, I just mean the sort of ridgeline in density in the full six-dimensional density space. So this is slightly more correct than just fitting in orbit, but it becomes an ill-defined procedure if the stream is not just this simple, thin, linear structure. If it has more complex, if it widens morphology by widening, or has gaps, or has been interacting with other things. So I think the goal is to move towards this last point. So these are sort of increasing complexity and computational time, which is to model the full stream density, meaning the full six-dimensional phase-space distribution function of all the stars in the stream. This is very hard. It's challenging to execute. I'm going to talk a lot about this at the end, so I won't say too much more about that now. But I want to show you a few examples of why these first two things might not be as applicable to the streams that we see in the Milky Way, because it turns out, if you look in detail at all of the streams that we know of, they all look extremely complex. So as soon as you can get below the initial low signal to noise view of what the streams look like, and you can see higher contrast views of the streams, they have very interesting morphologies. And there's a few different dynamical processes that contribute to, or phenomena, I should say, that contribute to how messed up streams can look. So I want to show you a few simulations that qualitatively highlight some of these different effects. So to start with, this is a simulation of a low mass star cluster, 5 by 10 to the 4 solar mass star cluster, in a spherical NFW dark matter distribution, smooth, purely smooth. This is the final location of the progenitor star cluster. These black points are the stars that are tidally stripped. And in this particular case, it's in a spherical potential, but relative to the coordinate system I project on, it's actually slightly inclined in the orbit. That doesn't matter for this case because it's spherical, but in these other cases, it does matter. So these are some different effects that can act to make stream tracks and stream densities much more complex. So in the top right, I've taken the spherical mass distribution for dark matter and I've made it triaxial. And in this particular gravitational field, the orbit that the cluster is on, right, I've made sure that the progenitor ends up in the same place and the orbit over the last orbital period or so all look roughly the same. In this particular case, this orbit becomes chaotic, strongly chaotic. And when that happens, nearby orbits, so the stars that are stripped from the progenitor cluster on nearby orbits in an energy sense, they end up spreading out or fanning. So the only dense part of the stream ends up being the stars that haven't yet had time to spread out because of the chaotic timescale of the system. So that's one thing that can happen. That can act to reduce the density of stars that were tidally stripped early on in formation of the stream. So in the bottom left here, I've taken the spherical dark matter distribution and I've added a disk. I've added a component, time-dependent component to represent the galactic bar. In this case, again, the orbit is inclined relative to the XY plane, which is the plane where I put the bar and the disk. So every time the stream progenitor comes into the galactic plane or comes near to the galactic center, the bar is in a different orientation, and depending on the pattern speed of the bar, it can torque the stream at different angles and with different magnitudes, depending on how it's oriented. So I'll talk a bit more about one stream that we think shows signatures of interacting with the bar, and a little bit more detail about what can happen. But you can see right away that some very complex things happen to the phase space morphology of the stream. And if you wanted to fit a track to this, it's not really, or an orbit, it's not clear what you would do.
Is there a bifurcation at the end of that arm, or is that just
Right here?
No, the other way. Their arm.
Here.
Yeah.
Yeah.
That is real bifurcation.
Yeah.
It's not just.
Yeah. A fourth thing that can happen, so now I've taken static spherical NFW and I've put a single substructure in it, 10 to the 6 solar mass, very dense object, and I have it impact the stream right here. And in this view, at least with points, you actually can't really see the difference. But if we zoom in, you can see, compare this one to this one, that impact causes a underdensity or a gap to form. And it can kick stars sort of out of the main track of the stream. So this is the case if you have a single perturber, what the types of things that can happen to streams once you have live substructure flying around. So you can see going from the sort of thin linear track that you get on a regular orbit in a simple potential versus chaotic, where the stream stars tend to spread out and become more diffuse much quicker, to cases when you have the bar where lots of very crazy things happen, to a situation where you have a substructure that perturbs the stream.
So can you distinguish, right, just looking at regular and chaotic, if you just increase the velocity dispersion, binding energy of the halo,
Yeah.
it also spreads it.
Well, it spreads out in a different way though.
That's
Yeah. So here you can literally, you just have to maintain the same energy, but you can spread arbitrarily in your other conserved quantities if you have any. If you just increase the dispersion of how stuff is stripped, then obviously you have different properties for what you have to obey. So you might only be able to distinguish those things if you have infinitely precise data, but there is different physics that reduces the spread. Okay, so why am I talking about all of these things? So I'm particularly excited because there's actually streams in the real universe around the Milky Way that we think show signs of these, at least these 3 different things. We actually don't know of any streams that look like that, a nice regular long thin stream. And so I want to give you 2 examples just to convince you that these more complex dynamical phenomena can actually happen. So the first stream I want to talk about is this one. It's called the Ophiuchus stream. It's that little, now that many of you have been trained from my initial slides, you immediately can recognize the stream in the center here. It's this very, very short little black strip of stars here. So it was discovered in pan-stars, so just from purely photometric data. So there's no kinematics that goes into generating a map like this. I remember when it came out thinking, great, a 2-degree long stream, that's not going to help us at all in constraining the Milky Way, so it's uninteresting. And then now I've written 3 papers on this stream and I've won more awards. So clearly something has changed, and I'm going to tell you why my opinion has changed about this stream. And I think it's actually a very important clue, or sort of a Rosetta Stone for understanding some of the more complex dynamical processes that can happen to stellar streams, and things that you might read about in textbooks that could happen on galaxy scales. So this is the stream as it was discovered in pan-stars. And I'm going to show, there's no stream here yet, but I'm going to show you how you can do slightly better in selecting stars if you include Gaia data, cross-match between Gaia and pan-stars. So first of all, some of you, the few of you who are astronomers will notice that these values of these 2 numbers means that this stream is actually somewhat close to the galactic center. So that means that even with the Gaia data, it's a fairly high density background that we're trying to contend with. So we're never going to have a crystal clear view of the stream unless we do even more follow-up. But here I'm using the Gaia data to further clean some of the foreground, and then primarily using the photometry to select out stars. So you can see the main dense part of the stream here, but you might also see that there's a little bit of an extension of the stream to the left here, and that's sort of it. So you can see it a little bit better here if you include a sliding selection and then change the stretch a little bit. Yeah?
So it seems like the noisy background structure sort of consists of arcs.
Some of it, yeah.
Is that just the noise properties, or is that other structure that's...
Yes. It's both. So Gaia, one of the issues is that the way Gaia scans the sky, it introduces some artifacts that can look a lot like arcs. So because this is pan-stars, which is deeper than Gaia, cross-matched to Gaia, at the faint end, you will see noisy things that look like arcs. But this is towards the galactic center. That's where the stellar density, even in the halo, is highest. So we do think there should be a lot of streams in there. And in fact, many of the streams that have been discovered over the last couple months are in exactly this region. So I don't have an exact answer. It's both, really.
Okay.
Anyway, so even with Gaia data, and I've actually, I've extended this to show a much larger region, you don't see many other stars associated with this stream. And that's very strange. So let's think a little bit more about the context of where this stream sits. So if you select out, instead of looking at main sequence stars, which is what we're looking at here, you instead look at slightly intrinsically brighter stars, BHB or blue horizontal branch stars. You can actually look at the proper motions of individual stars, and those are still pretty useful. And it also means that even though we don't have parallax information for the individual stars, we can use their absolute magnitudes, because they're on the horizontal branch, we can use the absolute magnitudes to get distance information. And if you do that, and then transform to galactocentric coordinates, those blue points, the BHB stars, and now project into the XC plane. So this is away from the galactic plane, and this is towards and away to the galactic center. The sun sits at minus 8.1 something here, kiloparsecs. This is where those BHB stars are. So right away you can see that one of the reasons that the stream appears so short on the sky is actually because we're kind of looking down the barrel of the stream. You can detect a very, very strong distance gradient from one end to the other of the stream. So it actually is a little bit longer than if you just take the angular size and multiply by the distance, because of foreshortening. For these stars, you can then also take the kinematics from Gaia and some follow-up that we've done to get radial velocities, and you can just numerically integrate their orbit backwards for a little bit and see where they came from. So that's sort of an indication of where what orbit the progenitor of this stream was on, since we don't see a clump that could correspond to the final position of the star cluster. And this is what the orbit looks like. So it has a fairly close pericenter, 3.5 kiloparsecs, fairly large apocenter, so it's a very eccentric orbit. And it's mostly in this XC plane, meaning it's coming in and out of the center of the galaxy perpendicular to the disk. perpendicular to the bar. And so every time it comes through this central region, it's feeling the gravitational influence of the bar at different orientations, which can cause very strange things to happen for stars that are being stripped from a cluster that's on this orbit. I should say that we don't actually know the properties of the bar, the dynamic properties of the bar very well in the center of the galaxy. We think it has a mass that's between 1/10 of the mass of the disk and 1/5 of the mass of the disk.
What
So-
about the length? The
Say again?
length of the bar? What about the length?
Yeah, I mean, that
Does it-
depends.
Does it, make any effect on the orbits if you?
Yeah,
short
it
bar?
certainly would. If you had a very, very short bar, then it wouldn't. But I think, I mean, the range of lengths is between 3 and 6 kiloparsecs or so. So it's still, its pericenter is essentially within the orbit, the edge of where the bar is. So we still expect it to have a strong effect.
Even we don't know like the full potential of the Milky Way,
Yeah.
how far can you integrate backwards and still trust it?
That's a very good question. I don't even trust this orbit. This is for like 2 periods, essentially. One orbital period is about 200 megayears, so this is less than half a gig year. There's no real answer to that. I wouldn't even really trust it once you go past the disk, because the model for the disk that I put in here is not very good. But it's not going to, like, these numbers are not going to change by an order of magnitude. They might change by a factor of 2 or 1.5. And on the pericenter, it's actually roughly at pericenter right now, so we know it can't get farther away. Like, its pericenter can't be closer or farther than 3.5. Or I guess it could be closer. Yeah, so that's a good question, given that we don't know the overall dimensions.
Oh, yeah, variant on that one, basically, like, if you vary the parameters of the galaxy within our knowledge,
Yeah.
how does that graph change, like?
Yeah. So I would say one of the biggest things that you could change, that's the dark matter distribution I put in here is spherical. We know that at least in this range, within 10 kiloparsecs or so, it looks like it's more flattened than that. So that would compress the orbit a little bit in that vertical direction. These parameters, though, those wouldn't change by more than 20%, I would say. Cool. Any other questions? Good. Okay, so what does this time-dependent component, even though we don't really know its parameters, we can explore what setting the parameters at different values does to this orbit and try to get at the question Shirley was asking. What does the bar do generically? Because the orbit of Ophiuchus is basically perpendicular to the bar actually induces a lot of chaos in the inner region of the galaxy. So this is that same orbit, this orbit, now integrated for much, much longer, and you can sort of see the irregularity in the apocenters and the pericenters, and David is crunching his face, do not believe that.
I do believe it.
Okay, good.
But I'm just wondering why it survived so long.
The bar.
No, the Ophiuchus.
Ophiuchus, that's another puzzle. Let's go back to that. How it even got to where it is, yes. But the point I just want to make here is that because we don't know the parameters of the bar, we can change them and see how chaotic the orbits are. And if you vary the pattern speed between, say, 30 kilometers per second per kiloparsec to 45, even beyond, that just makes this worse. You can compute how chaotic the orbits in this region are by measuring something like the Lyapunov time. What you generically find, there's a few resonant orbits that stick out here. This is the orbital period of Ophiuchus. What you find is the Lyapunov time, which sort of sets the characteristic timescale over which chaos is important, is often comparable to the orbital period or a few times the orbital period. Meaning that debris that's being stripped from a star cluster on an orbit like this is not going to stay coherent. It's going to very quickly spread because the orbits will diverge, which is what this is a measure of. So
What's the mass of the bar that you put in there?
5 by 10 to the 9.
And then how does it compare to the rest of the potential?
But the disk in this case is 6 by 10 to the 10. So it's small as a 10th or so. Cool. So yeah, here I've kept the mass fixed. But you could do the same thing, but a 2D grid where you vary the mass and the pattern speed and see what happens. And to get at Elena's point, here changing the pattern speed, I also scaled the bar so that it doesn't extend beyond where co-rotation would be for that pattern speed. It's still a very toy set of calculations and simulations. So just to remind you, why should we care about dynamical chaos? Here, the chaotic timescale is very short. It's comparable to the orbital timescale. And when that happens, strong chaos can have a severe effect on the debris that comes off of tidally stripped systems. So this is the best view of Ophiuchus we have, is this short segment and then possibly an extension here. You don't see anything else on this side, even if you expand this view and do a more uniform filter. So these are just a few different qualitatively different simulations of star clusters disrupting on some of the orbits that I showed you with Lyapunov times before. So in the top case, this is when you don't include a bar in the gravitational field. You start with a stellar cluster that's 10 to the 5 solar masses, and you slowly shrink the mass of the cluster until it fully disrupts sometime recently, so you no longer see the cluster left over. So this is no bar. And then these are 3 different bar models where, so this case is just for fun, just to show you some of the absolutely crazy things that can happen because of how chaos can deform the morphology of streams. But generically, if you look at all of the different bar models and what happens to streams, you tend to create diffuse material around the stream. So you're not just left with this nice thin component that you see in the case where there's no time dependence. You also have this lower surface density stuff around the stream. And you also can create apparent truncations in the stream just based on the fact that once you phase mix about an orbital time away, essentially the Lyapunov time, the orbits will very quickly diverge. Yeah?
So it looks like none of those examples stop as suddenly as the actual data does. Is that just because those examples are shown?
This is just this is not. I'm not trying to say this is the model of Ophiuchus. It's just to show you sort of what qualitative phenomena could create morphologies like this. That is a very good question and point. So here's if you take those simulations and you downsample them to have the right number of stars in this region as we observe, and then you had a background that has the same, I'm assuming uniform density, but the same rough fluctuations as the background that we have here. This is what you would observe of these. So in the case, basically in all cases, you expect there to be some kind of extension further down here. In the cases where you have the bar, though, sometimes you do end up quickly pushing stuff away from these nearby regions, whereas you would not expect that for the case where you don't have a time-dependent perturbation. Yeah.
Yeah, and also you've chosen this window here, right?
Oh yeah.
But it looks like these things will continue outside the window.
Yeah, I should expand that view. This one, there's like a segment right here, and then it kind of stops out. You don't see any more beyond that. But
so
absolutely, you're right.
To reproduce the observations there.
To reproduce the lack of stuff here.
Yes.
Yeah. I don't have a solution.
All right, so you haven't been able to reproduce it.
No, not with this bar model.
Well, some people suggested that it's got to this orbit very recently, right, and that it's just very dynamically young and disrupting. But that's a solution that could have no.
Well, that doesn't explain this then.
Yeah.
So another possible solution, which is I think even more special, is that it's on a perfectly resonant orbit, so that it always interacts with the bar at the same phase, and that can actually trap stars so that they can't actually get beyond a certain point. But we know that there's at least some extension. Actually, I said that we can't do better than this contrast with the Gaia data, but we've been, not we, I should say, Nelson Caldwell has been doing spectroscopic follow-up of stars in this region. And if you then ask, now you have added dimensions, you have radial velocities, you have chemistry, you can ask, what does the morphology of the stream look like if you take these extra dimensions into account? And these are the stars that have similar chemistry and very large radial velocities, like the stream does in this region, based on the follow-up that we've done. So you do see this extension in other dimensions as well, and possibly very, very low density extension right here. We haven't yet done this part of the survey, but that's the plan. Anyway, again, I'm not saying this is the solution for Ophiuchus, but this is something that can impact the morphology of streams and make it harder to make inferences if you just use simple models like fitting a single track or a single orbit to a stream. So for Ophiuchus, this short stream has a very abrupt density truncation with possible low density material around it. Generically, even if you vary the bar parameters, the orbits in this inner region tend to be strongly chaotic. So we think chaos can have an important role on the morphology of streams that are towards the galactic center. And in this case, what chaos does is can cause these low density plumes or fans to persist around the stream. So we're doing more follow-up to follow up that other side that Sigurd is interested in and let you know what we find. So now I want to switch to another stream that shows a sort of qualitatively different set of things that can happen to stellar streams. So in the first case, Ophiuchus is what happens if you have sort of large-scale time dependence or resonant time dependence in the gravitational field. I want to talk now about the GD1 stream, which has been a lot of fun to work on and very exciting over the last few months. So this is, again, with your specially tuned astronomer goggles. You can see the stream right here. I'm recreating what the stream looked like pre-Gaia, when you only had photometry, and the only thing you could do is select out a matched filter and isochrone, using some isochrone to try to see the stream. And you then only really see it if you bin the stars and try to smooth the background a little bit. This is what you see if you instead filter using the proper motion in the astrometry to get rid of all the foreground stars. All these black points here are individual main sequence stars in this field. This is a rotated coordinate system so we're trying to roughly put the stream along latitude equals 0 here. Notice it's extremely long relative to Ophiuchus, which is just 2 degrees. And the reason we can do so much better for GD1 relative to Ophiuchus is GD1 is basically, in a galactic sense, straight up. So Ophiuchus is sitting right over the bulge. Stellar density is very high. Even with Gaia, the contrast is low. With GD1, we have this beautiful, like right here in the background is a few stars in the center of the stream. And that's because just essentially where you're looking in the galaxy. So one of the things I'm pushing on right now is improving density models of data that we have so we can make more robust comparisons to the models that we generate. So this is an example of building a constrained Gaussian mixture model with a background of the density variations along the stream. And so you notice a lot of interesting features. There's these underdensities that appear, and most excitingly, there's this spur of stars that sort of juts out roughly parallel to the stream that you wouldn't expect from a sort of a simple model for how a stream like this could form. So to emphasize that point, so this is the data zooming in on that central region where that spur feature is. This is a model for the formation of a long stream like this, where you take a star cluster, you fully disrupt it some amount of time in the past, 500 mega years or so, and then because the cluster fully disrupts, it's no longer releasing stars, so the two tails aren't being populated anymore, and they can phase mix away from each other, leaving a single gap, or an underdensity. So this model is just meant to reproduce sort of one of these underdensities, and to highlight the fact that you don't then naively expect to see spur features that jut out, or other strong density variations like we see in data.
So we, sorry.
Yeah.
What drives, what sets the position of the gap then? The original position of the progenitor? Or
In this case, it was me. Oh yeah, this is where the progenitor would end up, and I just tuned it to end up there.
So if you just generate stars, I don't know how many stars there are in GD1, more or less.
How many do we observe? Like 1,500, 1,700.
If you, shed noise, can
Yeah.
you also get gaps?
I don't have a plot to speak to that point, but yes, you can get smaller underdensities, but they're never this large in general. Yeah.
How are you like cutting all of the extra stuff? You have a lot more stars that are, at each end that aren't on that stream.
You mean over here?
Yeah, exactly. Well, kind of both ends, right? Are you allowing it to flare
Oh,
out,
sorry,
or
yeah. I'm assuming that all of this and all of this is just, because it's so long, you actually start to see the disk come in on either end, so I'm assuming that's all background. It's a good question, is it background? Okay, in the interest of time, let me just speed up here. So why could there be gaps or these underdensities and a spur-like feature that you wouldn't expect from a simple simulation like we showed before, which was in a static, smooth gravitational acceleration? Well, some people a few years ago ran simulations of streams forming in a live dark matter halo where you have substructure flying around. And what happens when you have substructure is through impulses that happen on the stream, you can kick stars out and form little underdensities based on essentially flows that make stars move away from the impact points of where substructures interact. So to show a little movie of how this can happen, so So this is a very, very simple model for a stream. We're going to be in the rotating frame, so the stream is actually moving around, but we're rotating with it. And I'm going to impact the stream at this small point right here with a very, very dense perturber. So what happens initially is you form a loop of stars. So the things that receive the largest impulse start precessing and move away very quickly, but because they're all moving on epicyclic orbits relative to the orbit of the stream, they maintain some kind of coherent shape or structure in this very, very cold model for a stream. Notice very early on, though, the impact causes these little spur or arm-like features to appear just on either side of an underdensity or a gap. And if you could measure the velocity offsets of stars in these structures relative to the stream, that gives you information about the geometry of the encounter and the properties of the subhalo or the perturber that caused this gap to form. So here's the data that, based on the density model, is, yes?
How complete is that set of stars? Like, we get observations, can we get more stars?
I was hoping to slide that under the right. Actually, from the left of here, there's a lot of wiggly density variation that's just due to the Gaia scan pattern. But the entire stream, the best we can do with Gaia and pan-stars is just down to what Gaia can see. So it's only down to 20.7 or so. So if you go much deeper, you can get a much higher signal-to-noise view of this.
Okay.
Anyway, we have models for GD1 that, once you include a perturber, can produce features like this. And so this is very interesting because A, the stream does not anymore follow a simple track. There are density variations that can jut out of the stream. But this also is exciting because it gives you, it's a way of possibly constraining the nature of small-scale dark matter. So if this perturber was a subhalo, for example, we would be able to, by measuring the velocity offsets, we can constrain the properties of that substructure. All right, let me jump.
So is that the parameters of the perturber that you put up there to generate that cap?
Yeah.
So what sort of dark matter object is 15 parsecs? I don't know what the impact from 15 parsecs.
Okay. So if you marginalize over the orientation of the encounter, so this is work that was done by Anna Venazza and David Hogg and I. If you marginalize over the other parameters of the encounter, then this is the sort of region of space that produces a spur and a gap. Those are the only criteria we use in exploring the different models. This band, you can also think of this in terms of density. This band is the sort of mass-size relation you'd expect from CDM, cool dark matter. And then these other points are luminous things around the galaxy. So it's consistent with supermassive black hole. Cool. So, cool. So I was going to talk a little bit about stream density modeling, but there have been some good questions already, so I don't have time to do that. So I just want to leave up some key points here. So one is that stellar streams, because they provide information about orbits, time-dependent information about the Milky Way, they can deliver precise constraints on the distribution of dark matter around the galaxy. We can actually do this using the data we have in hand now or over the next few years. I showed that some of the streams that we observe around the Milky Way that we thought were nice, simple, linear structures like GD1 actually have complicated density variations and other intricate structures, which may be clues towards other dynamical processes that are changing morphologies of streams that form. And that's generically true. I could show you basically for all of the streams that were in the field of stream, something weird about the stream that makes it hard to do simple track fitting or orbit fitting. And so in the future, this is going to be a challenge to sort of make sense of what's weather and what's climate for trying to learn about the overall structure of dark matter. Lauren liked that. But it's also very exciting because this is one of the few channels we have towards actually constraining the very, very low mass end of dark matter physics, which might be the only way we can rule out different theories. So I'll end there.